Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future to the, not the final lecture, because the final lecture will be next week, but it's the final lecture with actual material to the lecture, because next week will be more fun. Like we'll have a recap of everything we've been doing in the semester. There will be a quiz. Ijskage 100, who know Ijskage 100 on TV? Still no. Okay, so we'll play that with the quiz. You'll play against the TA team and we'll see who wins. But this week we'll cover more material, also normally taught at the master's level, but I know that you will make it. I'll try to explain it as simply as possible. I have a question for you that I will ask first. Simple one. There you go. Can you remember last week and the week before, what fundamental rules of probabilities did we use and apply to information retrieval? Bayes rule, partition rule, pigeonhole principle, the addition law of probability. Right, let's look at your answers. All right, we have a majority with Bayes rule. Yes, but oh wow, and somebody changed their minds. So indeed, Bayes rule is this magical device that allows you to compute something completely impossible just by swapping the sides, and suddenly it becomes easy. And we'll have it again today. Do you know what the pigeonhole principle is? Also known as Dirichlet? Never heard? It's very powerful. It's very simple and at the same time very powerful. Basically, it says that if you have 10 boxes and 11 objects and you put them into the boxes, there will be at least one box with 2 objects. It's that simple, and yet there are many, many things in mathematics that you can prove with that. But we did not use this principle in the probabilistic retrieval lecture. All right. Let me now switch back to the topic of interest for today, language models. So let me start with something that should be familiar to you, which is this thing right there. Who recognizes this? You've seen it before, right? This is all in the context of grammars, and you have plenty of equivalent things, right? You have the notion of a language, that is basically a set of strings. And then there's the notion of recognizing a language, accepting a language. And then you have many ways of doing this. You can use this sort of machines here, the finite state automata. You can also use regular expressions that are not to be actually equivalent to this. And then you have many, many improvements over this. You can have the non-deterministic automata. You can have the ones that have a memory with a stack, the push-down automata, I think they are called. And then on the other side, you have the notion of context-free grammars. Who heard of that? I'm sure you did, right? With EBNFs and so on. So any compiler needs that sort of things, right? And so if we then look at one of these, this finite state automaton right here, can anybody tell me the language in a regular expression that recognizes? Yes, maybe we have the microphone.
Is it on? Okay. I'm not sure about regular expressions, but it's a B, then you need 2 A's at least, basically.
Mm-hmm. And then A's. Yes, exactly. So it's BAA star, basically the real expressions. Yes, but this is exactly it. So as a refresher, this is just the drawing, so the visual of that. But basically what there is this idea of a state. Every node in this graph is a state. And we have transitions from state to state. In that case, the transitions, so they are the transitions are based on the letters that you consume of your alphabet. And given a state and a letter that you consume, you go to another state, right? So typically you have a matrix like this that tells you the state you come from, and then if you consume A or if you consume B, where you go to. So this is where you are, and this is where you go to, depending on A and B. For example, if you are in state, let's say 3, and you consume an A, you go to state 4, right? So state 3, you consume A, you go to state 4. So that's just a different formal representation as a matrix. But this is the same thing. So you have a starting state. This is where you start. You have the final state or final states. This is where you must be in order to accept the world at the end. And this is not actually part of the formal design, but this is common practice, that this is called the sink, that you basically land everything in there, and then you put this cycle with all the letters, right? So technically, you don't need that as part of the formal definition. It's just a design principle. All right. So this is a finite state automaton, and it's actually beautiful. So let's actually play with this, because the advantage of this is that you get beautiful animations. So you can visualize it with light bulbs, right? You basically switch that on. This is where you start. So you start in here, and then you put your cursor at the beginning of the world that you want to consume, right? With full of B's and A's. All right. Who thinks this will be accepted? Who thinks it won't? Oh, okay, so it's leaning towards accept. So let's try this. So we are going to move left to right here and consume the first B, and then we go here, right? You agree? We just switch off the light on the left, light it up on the right, and we go here. So we just move around. Then A brings us here, A brings us here, and then we just stay here because of the transition. And then we are in the green because we accept here. This has succeeded, right? So we accept. So this is how it works. Who thinks this will be accepted? Who thinks this will not be accepted? Okay, and you're right, so let's check. So we start here, then B, then A, then B, and then we are in the sink, so that's already over anyway, but let's still do it. So A rejects, okay? So that's basically how it works. Now it's a deterministic finite state automaton, because there's only one light bulb at a time that is on somewhere, right? Non-deterministic, you can have multiple of them, but as you might have learned, you can actually make it deterministic by taking the power set, right? Who remembers these things? Right. Okay. So this is a very exciting topic. All right. So this is rejected. Now, if you want to be even more formal, you have all of these Greek letters that you need in there, with some set for the alphabet that is typically called sigma in uppercase. Then there is the set of final states called F. The set of states is called Q, right here on the left, uppercase Q. And delta is used for the transition function, right? So delta is a function that takes a state and a new letter to consume, and it gives you the states that you go to. The idea of that is actually not very far away from a Turing machine, right? Also in a Turing machine, there's the idea of transition, but except of going from a state to a state, you just go left or right on the Turing machine. All right. Now, the reason why I showed you that is that I would like to give you a different perspective on these things. You know that when you have an air conditioning system, you can revert it and use it to do heating, right? You can reverse the whole thing. And in fact, in that case, we can do the same sort of things. We can actually reverse the way that it is used, because the way it's used here, it's consuming a world, right? If we could tweak that in order to make it generate worlds, probably you see it coming, right, where we are going to, right? But let's turn it into a generative thing that we can create worlds with. So what does that mean here? We have some language space. That's basically the theory of languages and regular expressions and so on. So let's call it L. That is the space of all possible words that you want to accept as part of your language. So in that case, I put some words that are accepted. But now instead of calling it L, I'm going to call it omega, which is the set of all the possibilities that we actually have, right? Everything we can generate. And that means now we have an omega, we can actually put probabilities in there, right? We can actually put a function P that gives a weight to every one of these words in the language space, right? Now, so let's call it back L. And that gives us this, right? So we have a probability distribution on the on all of the worlds. Now, given that I gave you this, that we can look at it from a probabilistic perspective with a probability distribution on the worlds, can we turn this into a generator? Does anybody have an idea how we can do this? How we can augment that automaton? Several answers? Do you want to answer too? No? Anybody? I'll come to you if nobody else. Yes, over there. Trying to rotate a bit. All right.
Instead of assigning just a letter to each space, we can assign a probability on the transition that a certain letter is taken.
Mm-hmm. Exactly. So like I did here, right? Adding, so I just put 1/2. It doesn't have to be 1/2, but I did it here. So here, everywhere I added these 1/2 weights to every letter. So A is generated with probability 1/2, B with probability 1/2. So that's exactly the idea that you are suggesting, right? I also added something. Look at the right, what I did. This is a bit special because at most of the nodes, you have only the choice between A and B, right? But on the right, I did something a bit special on this final set. Why did I do that? Because if I only put 1/2 here going here and 1/2 going there, do you see that this will never end? I'm going to just generate forever and ever and ever and ever and ever. So I need it to stop somewhere. So I need to add some probability that it stops. This is the P stop. I will call it P stop later. So here I just put 1/4 stop. Then what quarter B? It's all arbitrary. There is no particular reason why I put 1/4 or 1/2, right? Put whatever numbers you want. But it just should sum up to 1 based on every state. Okay. And now we can go ahead, probably start at the start, and then roll a die, roll a die, roll a die, and just generate things. Let's do it. So let's roll a die. Okay, I got a B. Probability 1/2, then I got an A, then I got an A, then A, bam. And now I stop, right? If I had instead generated something that goes into the sink, it just goes on forever, but basically I'm unable to generate something that would be accepted, right? Okay. So I could also tweak the whole thing, by the way, in the sink of removing this A-B loop and just putting something that says it's over, it's rejected, right? And then you start you start again, like when it's game over and you need to start the game again. Okay, so this word gets generated with a probability of 1/64. Why? Because I multiplied all these things. There is 1/2 to generate B, and then 1/2 to generate A, 1/2 to generate A, so that's 1/8 already, then 1/2 to generate another A is 1/16, then 1/4 to stop. 16 times 4 is 64. Who agrees with this computation? Did I assume something here? Yes? Maybe the microphone, could we? There you go, thank you.
I mean, overall possible generations, it's 1/64th, but if we don't output the generations that are not valid, then that should change the probability of the
Yes, this is true. You should renormalize. There is some more work to do to renormalize the whole thing, right? So basically, this is called, in quantum foundations, this is called the post-selection. It's the idea that you go ahead and do something, and it succeeds, that's fine. If it doesn't succeed, you just ignore it and throw it away and start again. If you do a post-selection based on the fact that it succeeds, then it did. You will not get the 1/64th. You will get something renormalized, maybe a bit higher. Right. So 1/64th would be the probability that we actually end up generating something valid, and it is BAAA, right? That's the way to formulate it. All right, but I assumed something else because I multiplied all these things. Did I? Yes?
You assume that they're independent, the probabilities.
Exactly, I assume they are independent. I assume that every time I arrive on a state, I just toss a coin again, and independently from everything before. This is a very important assumption. Otherwise, I would not have been able to multiply in this way, right? So this is the reason why I can do that. All right. So now, I'm going to connect things with what we've been doing last week. Because now, here I generated words that have letters, right? I consume letters, and that gives me a word. But there's another way to another level of granularity you can do that with. Instead of words, you can have sentences, and instead of letters, you can have words, right? So B would be a word, A would be a word, and you put a space in between, right? So it's just the same thing. It's a bit the same difference between the byword indices and k-gram indices, right? With the byword indices, you have pairs of words. With the k-grams or bigrams, you have pairs of letters, right? So here I'm just doing a small shift of perspective that on the transitions, on the edges, I no longer will have letters, but I will have words, full words every time, right? And I get a full sentence as a result. So now, if I use this automaton in a generative way to actually generate, so not words, but full sentences, word by word, that gives me a probability distribution over these documents, and you might recognize here a random variable, right? This gives us a random variable that takes its values in the documents, and this random variable has a probability distribution. But there is always, when you have a random variable, this is what we saw last time, there is always an omega space somewhere. And that omega space here is whatever it is, it's just some underlying omega space, but basically whatever we do, every occurrence of every elementary event will give us a specific random document. In order not to confuse you, I was careful, I even redid the slides to use the same letters. So you might remember that last week and the week before, I used big D for the document random variable, right? So I'll do the same here. I'm also going to use big D. But there is a difference between documents this week and last week. Do you notice a difference in the model of the documents? Let me formulate it this way. Last week, for probabilistic information retrieval, did we assume set of words, bag of words, or list of words? Do you remember that? Did we care about the order? Did we care about the occurrences last week? Yes? Exactly, it was set of words. You're absolutely correct, because we had vectors of Booleans, right? If we have vectors of Booleans, this is just sets of words. Either a term is in a document or it's not in a document. So indeed, it was the set of words. Do I have sets of words here? No, I have lists of words, right? Because here I generate things in a specific order, right? So it's B and then A and then A and A. So now I have lists of words. So this means that I still have a random variable that takes its values in the set of the documents. But now the set of documents, it's no longer to be the set of Boolean vectors, as it would be with the set of words model. Now we have a list of words model, and with the list of word models, this is more like the set of all sentences you can generate, right? And you remember this little star here, the clean star, you remember it just basically denotes the set that you can get if the alphabet is T. So that would be the set, I use the T for terms, right? Like term frequency and so on. So T for term, T is the set of terms, maybe, I don't know, 500,000 of them. And the star just gives me any finite length sequence of terms. This is what T star is. It's any sentence, basically, any finite sentence. And I told you that a random variable is neither random nor a variable. It's just a function from the omega space to the set you want. So here we just have D as a function from omega to the set of all documents in the list of words meanings. Who is following? Right? So D is still denoting a random variable that's a document, but with the list of words model. Very important. Since we are talking on list of words, but actually it would be the same with bags of words, I can talk about the length of a document, right? The length of the document is just the number of words in it, right? So I'm just going to give it a name because this is also a random variable, right? It just turns out to depend only on D, right? But it's a random variable. So let me call it LD in uppercase, right? So LD is a random integer, actually. It's a random integer because that's the length of the document I generated. Okay. So now, here's the cool thing. If you take a document, anything, so I basically use this as an example, maybe that wouldn't be the way to go, maybe a book like I give you, like all Sherlock Holmes and so on. So if I give you the whole text file with all the Sherlock Holmes, who is able to turn this book into a model, a generative model like this? If I give you a book, who can do this? Any idea? Yes?
We could just take the chain of like all the words in the book and assign probability 1 to each transition.
So you would look at the chains of words, right?
Yeah.
Of a specific length, for example, a sliding window, 2, 3, and so on. And you say you assign probabilities. Based on what do you assign the probabilities?
Based on the transition from one word to the next. So like
yeah.
Probability 1 if the transition exists and 0 if it doesn't.
Probability 1 if it exists and 0 if it does not exist. Yes, almost. You're just missing a renormalization. Because if you imagine, for example, you have, I don't know, let's say you take a window of 10, then you have 9 words, right? And you want to guess the 10th one. So if you would assign a probability of 1 that it exists, no, that it doesn't exist, you're half of the way to doing it. I'm basically trying to exploit what you said without giving you what's going to come. That's what I'm trying to do, because of course there will be many slides that describe this. But you're close to the idea, right? You look at the document, you look at the chains of words that they are in there, and you try to infer the probabilities. In that case, actually, it's a simple case because we have an independence condition, right? So every word is independent from the other one. So do you see how, in that case, I could build a simple automaton that would be super simple, like just a single node that iterates over itself and that gives me a probability for the next word? Is there a simple way you could derive the probabilities from the document? Or anybody else has an idea? Yes, over there? Can you throw the microphone? Yeah.
If we had the positional indices, then we could count the occurrences of every term after one term and then assign according to this induced probability.
Exactly, that's exactly the way to go. You basically, if you want to take into account that a term is going to follow from another term, then you're going to look at every occurrence of the first term and then look at the number of occurrences of the next term after it, right? So this is what you meant? This goes exactly in the right direction. Now there is even a degree 0 of things. You can even not care about the term that there was before and just go ahead and pick a term, but just at random every time. And in that case, you can simply pick the term frequency, right? You just pick out a term. The probability is functional to the term frequency in the document. For whom is that intuitive? So if I'm going to have a very frequent term, it's going to have a higher probability of being the next one. If I have a very rare term that barely appears in the book, it will have a lower probability, right? So I could do something very simple like that. But again, I will have plenty more details. This is just the very general discussion at first. But anyway, now you probably get an intuition that we can build models based on the documents, right? There are plenty of ways to do that, but I could build a model depending on a book. And I can do it for another book and for another book and for another book, right? That I can derive a model like this. Now, if I try to formalize what probably you meant and you meant with this formula, we can try to understand it together. It's scary, but it's actually less scary than it seems. This is one way that we could think about it. So imagine that I have trained my model and I have my probabilities and so on. And I want to compute the probability that now that I try to generate a document, I'm going to get D1, D2, D3, right? I just call them D1, D2, D3. I'm trying to find something. It doesn't fit with the polyban because it's more than 3, but I don't know. Computers are cool. D1 is computers, D2 is R, and D3 is cool, right? So computers are cool. So the probability that the document I generated, big D, that's my random variable, the probability that it matches computers are cool is, and now we are going to use the chain rule. So first, you agree that in order to generate computers are cool, I have to have the length of my output document to be at least 1, right? Because if it already stops at 0 and it's empty, I will not get computers are cool, right? So in order to get computers are cool, I first need to know that the length of my document D is at least 1. Who agrees? All right. Now, given that I know that it's at least one, I also need the first words to be computers, D1, right? So look at just these two here. If I multiply them, what is another formula that is equivalent to this one? Multiplying this with this, what does it give to me? Okay, does it look better? Okay, awesome. Thank you for spotting this. All right, and you answered correctly that indeed, this is the chain rule. This formula here that says the probability of LD bigger than 1 times the probability conditioned on the fact that LD is bigger than 1, that D1 equals D1. This is the same as the probability that the length is greater than 1, hence D1 equals D1. Right? That's just a chain rule. Who remembers it? All right. So, for example, the probability that there are clouds and that it rains is the probability that there are clouds times the probability that it rains conditioned on the fact that there are clouds. That's the chain rule. And now I'm just using the chain rule over and over and over and over and over and over again. That's all I'm doing. Because now that you've established that the first two give us the conjunction that the length is at least 1 and D1 is equal to D1, I can then condition on that. This is basically what you said, and condition on the fact that the length is at least 1 and the first word is computers, D1, then I'm going to require now that my length is at least 2, given that it's at least 1 and that the first word is computers, right? And now I get the probability, if I multiply the first 3, I get the probability that the length is at least 1 and at least 2. So of course, this is enough, at least 2, and that the first word is D1, right? So the first 3 basically tell me there's at least 2 words and the first one is computers. Now, if we know it's at least 2 and the first word is computers, what's the probability the second word is R? That's the next P here. Because now we ask for the probability that the next word 2 is R, given that the length is at least 2 and the first word was computers, right? And again, here I dropped the length is at least 1 just because it's equivalent, right? If I say the length is at least 1 and at least 2, I can merge them in at least 2, right? I don't need the at least 1 anymore. Who is following until now? Okay, so now what do I have? I know that there's at least 2 words and it's computers are. We have a questions over here. Where is the microphone over there?
We've spotted another typo. In the 4th term of the equation, it says given and.
Given and, yes, exactly. I'll fix that as well. It's very important. That way it's done. And I know that it's all. That the length is at least 2 and the first 2 words are computers are. So now we need the length to be at least 3 to generate our sentence. So that's where the next one comes from. It's the probability that the length is at least 3, given that we already knew it was at least 2 and the first word is computers and the second one is R, right? D1, D2. Okay, now we have, if we multiply the first 1, 2, 3, 4, 5 probabilities, now we have the probability that it at least 3 and at least 2 and at least 1, but these are useless. And the first 2 words are computers and R. Who is with me? Okay, what's next? We need the third word to be wonderful, awesome, cool, cool. So cool. The probability that D3 is cool, given that the length was at least 3 and given that D1 was computers and that D2 was R, right? So now if I put these 6 together, I know that the length is at least 3 and the first 2 words are computers are cool. And the last thing I need is to stop. I need to know that given that the length was at least 3 and the first words are computers are cool, then the probability condition on that the length is exactly 3. That means it's not 4 or 5 and we stop here. All right? So this is here, the formula based on the chain rule without any assumptions of independence, because I have my conditions, that the document we generate is computers are cool. All right? Now I added these little colors here to say that the probabilities that the length is longer, that there is one more word, basically, this is what we mean. The probability there is one more word given the previous words, we're going to call it 1 minus p stop, because p stop is the probability of stopping. And the last one, the probability that the length is 3, given that it's at least 3 in the previous words, that p stop. And here I'm going to assume something. I'm going to assume that p stop is a constant and it's always the same one, right? So I'm saying that it doesn't depend on the length, it doesn't depend on computers are cool or whatever. It's just the probability of stopping. I call it p stop. And 1 minus p stop, it's because these are complements, right? It's complement even. Either you stop or you don't, right? So this is why it's 1 minus. Okay. So this is my general formula. Keep it in mind. This is fundamental. This is the most important one. Now, I'm going to make an assumption. So not on the p stops. So the p stops, that's it. We are done. But we still have these 3 probabilities on the right that we need to say something about. Because as you can imagine, now there are only 3 words. But what if I do it with an entire book? I'm trying to generate an entire Sherlock Holmes out of it. I'm going to end up with a condition on a million dn equals dn, right? We obviously don't want that because that would overcomplexify the system. So we have an assumption that we call the Markov rule. Who heard of the Markov rule? The Markov rule basically means that you forget old stuff, right? So it just means you remember the previous n terms, whatever came before that, you forgot, right? And what that means concretely in terms of conditions is that the probability that the next word is dk, knowing that the length is at least k and that these are the previous words from the very beginning, so it goes all the way to d1 all the way to k minus 1. It's the same as if you had conditions only on the previous n terms. Whatever comes before, you forgot. So the Markov rule just says this is equivalence. We forget the previous term. For whom is that intuitive? Okay. And now the parameter n can be anything. Can be 10, remember the previous 10 words, can be 2, the previous 2 words, can be 1, just 1 word before. It can even be 0. 0 means you don't even remember anything. Can you imagine reading a book like that? But yes, you could absolutely just look at the next word and you don't even care about what comes before that. Right? So this is a Markov rule with n equals 0. All right. Now, I have rewritten a formula, this time with a length of 4, d1, d2, d3, d4. Polyban is unexpectedly working. And then I replaced my probabilities of the length being 1 more with my 1 minus p stop, right? That's the red part here. And I have put my p stop at the end. And now my probability that the first word is polyban, the second word is depending, the first one is polyban. Then the third word is unexpectedly, given that the first word is polyban and the second one is. And then the probability that the last word is working. And you see what happened here? I forgot that I was talking about the polyban. Something is unexpectedly working. I don't even know what it is, because it only depends on before that we had is unexpectedly, right? This is because I assume n equals 2 with my Markov rule. And it's another way to say that we have 3 grams. You remember k grams? This is exactly what's happening here. I'm basically just having a sliding window of length 3, where the first 2 of my sliding window are the words that I remember, and the third one is the new word that I'm adding. So this is why we say k gram, 3 grams, 2 plus 1. We still with me? Okay. Who agrees with this formula here? Right? Makes sense, right? The probability we generate this, we just multiply the 1 minus p stop, then it's the probability, the transition probability. Okay. And now this is getting closer to the discussion we were having about how do we extract that from a given document. Well, now we have the answer. We just look at the 3 grams. We take Sherlock Holmes. We isolate all the 3 grams. And then we build the transition, the probability transitions, the numbers, based on statistics on these 3 grams. Right. That's how it works. All right. Now, I'm going to take a special case of n equals 0. Because this is actually quite interesting. It's a special case that allows you to simplify a few things. N equals 0 means unigrams. Unigrams because we're only considering the next word, but without anything before that. So it's unigram. So what happens for unigrams? Well, it means that we forgot everything. We can't even remember the words before. So the probability that the next word is dk, given everything that was before, is the same probability as the probability that the next word is decay. All we know is that there are at least k words. There is a next word. Right? So yeah, that's what we remember. And we call it P decay. So P indexed with the words, right? So P computers, P R, P polyban, P unexpectedly, and so on, right? So this makes it easy because there is only one parameter here. It's only the term. It's just a flat list of terms, and they all have a number associated with them, which is the probability. And this you can get from the term frequencies. P decay can essentially be taken as the term frequency of the document that you train on, just renormalize with the document length. For whom is that intuitive? Okay. Good. So this is what it looks like. Here I took some Shakespeare, and what came out of that is to be or not to be. So 2 has a weight of 0.3, B of 0.2, and so on and so on and so on. So now I have this Unigram model that is based on these weights. Who would be able to generate documents like this using this model? Yes. Many of you, because you just toss a coin every time, pick a term according to this distribution, and that's your next term. And then you do it again and again and again. You just don't look to what you had before. This is the Unigram model. Now, if I were to draw the deterministic automaton, this is what I would get, right? I have one state that is where I iterate, and then at some point I stop, right? So I don't have any sink here, right? That also addresses the problem that you mentioned earlier, that we could be land in a sink. Here we don't, we just stop over there, and we just iterate. Okay? This is a Unigram model that we can turn into a generative machine that allows us to generate the documents. Okay. Now, can anybody give me the formula for the probability that we generate document D1, D2, D3? Computers are cool. Under this assumption of n equals 0, the Unigram model, and under the assumption of p stop and 1 minus p stop that are constants. Can anybody give me the formula here using the PD case? I see one hand over here. Right, let's go to you. You can take the microphone.
So it would be 1 minus p stop times the probability that D1 is computers times 1 minus p stop times the probability that D2 is R times 1 minus p stop that times the probability that D3 is cool times p stop.
Yep, that's it. That's what you meant, right? Yeah. Okay. So this is it. This is the sequence of probability, the product of probabilities I get. Who agrees with that formula and what with your colleague said? Okay, wonderful. So this is it. That's the Unigram model. No memory at all. Now, there is something special about Unigram models. Is that if we don't have any memory, then using lists of words is a bit of an overkill, right? Because if we don't remember what happened before, there is no notion of order or no notion of lists, right? So we can actually, in the case that's only for Unigram model, it doesn't work for the other ones, bigram, 3 grams that you cannot do. But in the case of Unigram models, you can actually go from the list of word models to the, let me remember if it's bag or set, to the bag of word model. So we go to the bag of words model by, instead of considering sequences of words, I just consider a number of occurrences per word, but I don't know the order of the words. What did I write here? I wrote n to the power of w, right? It's just that we assign an integer to every word that there is in there. So we'll call it d prime. D prime is just some, it's d, but you forgot the order, right? Who understands that for every specific value that d prime can take, there can be different values that d can take, right? For example, computers are cool, or are computers cool? That's the same under this assumption, right? If I forget the order. So computers are cool, are computers cool? Cool are computers. Cool computers are, if you want to talk like Master Jedi, Master Yoda. So basically all these possibilities. How many are there in that case with 3 words? 6, exactly. There are 6 possibilities. So in that case, I have 6 documents with list of words corresponding to one under the bag of words semantics. Mathematicians would call it equivalence classes. You have an equivalence relation that 2 documents are the same if they have the same occurrences, and then you take the quotient set by this equivalence relation, and then you get D prime, right? This is what we do. And then how do you get the probability of the equivalence class? So the probability that we get computers are cool with these occurrences and under any order. We just take the probabilities of all the original documents. Computers are cool, cool computers are computers cool, and so on, and we sum them up. If we sum them up, then we get the probability that it is in any order. Who agrees? Okay. And this, what we need is the number of matching bags, because in the special case of the Unigram distribution, the probability that D equals D when it matches D prime, do you see it's always the same? It doesn't depend on D if you take a specific D prime. And this is because we use the Unigram formula. In essence, it's only because that commutes. Do you see that you can commute PD1, D2, D3, you can swap them, it's the same result. You get the same number. So do you see the order doesn't matter here? So basically, this formula here where I add P that D equals D, it's actually the same thing, just multiplied by the number of documents that match the occurrences. So it would be in that the case of computers are cool, it's 6 times the probability that I generate. So the 1 minus P stop, P computers, 1 minus P stop, and so on. So I need to multiply by 6. How do I know 6? Well, 6 actually comes from the multinomial distribution that you might have heard, or maybe the binomial distribution you heard of. So I'll come back to that, right? But I think you deserve the break now because I see that it's 11. So we'll continue that after the break and continue to try to come up with the formula here for the bag of words model for computing. So see you at 16 past 11 for the continuation.